As I said, we were going to start by talking about how we would use the principles we've just learned to calculate the static situation with this guy. So let's take a look. First of all, you determine if the system is in static equilibrium. In static equilibrium, the net force has to equal 0 and the net torque has to equal 0. There can be no acceleration, because if acceleration occurs, then the net force is not 0. And so in this case, what you're saying, here's the free body diagram, that these two forces, Fr and Fl, summed together are equal to and opposite the weight. So that's the net force is the same. Then you choose a pivot point and calculate torque for each of these forces that are present here. And the torque summed together has to also equal 0. So you draw the free body diagram, which is shown right here. And you then calculate and make sure the upward forces sum and the downward forces sum in such a way as the total is equal to 0. And you choose a pivot point based on your ability to measure distances such that it's easy to calculate the torque. Now, many times somebody will choose a pivot point where one of the forces is, because at that place the torque there is 0 because the distance is 0, and then all you have to do, for example in this case, is calculate the distance from here to here times this force, and that has to equal the distance from here to here times this force. And then you look at the solution and make sure it's reasonable. So here's another situation. Now it's a little different because we moved this over just a little bit. But it says calculate Fr and Fl if the hands are 9/10 of a meter apart, and the center of gravity, which is right here, is 6/10 of a meter from Fl. And the mass of the pole is 5 kilometers. Okay, or 5 kilograms, excuse me. So Fl plus Fr has to equal 5 kilograms. And you pick a pivot point either here or here, and you know that, let's say you pick this pivot point, you know that Fr times 0.9 has to equal the weight times 0.6. And that's what we showed right here. Fr plus Fl has to equal the weight, or 49 newtons. And in this case, we selected the weight point as the pivot point here. So it's -3, which is this distance, times 49, which is the total weight, plus Fl times 0.9 is equal to 0. And if you do the math here, Fl is equal to 16.3 and Fr is equal to 32.7. This is -3. The pivot point is actually right here. This is -3 and it's a downward. And then it's minus because this is downward, and it's plus 9/10 because it's upward. And the sum of those together is equal to 0, or you can set those two equal to each other. Now here's a nail puller, and this is an example, and we're going to start talking about simple machines now. And this is an example of a first class lever. A first class lever is where one force is on one side of the pivot point, and the pivot point's right here where this arrow is, and the other force is on the other side. So Fi is the input from the person's hand, and Fo is the output from the pry bar, and N is the force holding the nail in, and this is the normal. So the distance to the output is from here to here, and the distance to the input is from here all the way over to here. Here's another type of simple machine. This is a second and a third class lever. Now if we back up just for a second, remember a first class lever, you have the pivot point here, you have the input on one, or the output on one side of the pivot point and the input on the other side of the pivot point. With a second class lever, which wheelbarrow is an example of a second class lever, you have the pivot point is here, where N is. The output is here, and the input is over here. So what you see is that both the input and the output are on the same side of the pivot point, and the output is closer to the pivot point than the input. And that's what a second class lever is. The output is closer. So you put, and the torque from your input is this distance times this force, and the torque from the output is this force times this smaller distance. Now, third class lever is similar to the second class lever in that both forces are on the same side of the pivot, but the input and the output are reversed. Here, the pivot's back here. The input is actually closer to the pivot, and the output is farther away. It's over here. And so there's actually no mechanical advantage here. The reason that this is set up this way is for other reasons. And so you have R, this R times this F has to equal this F times this R. Similarly, this R times this F has to equal this times this. So this is a second class lever, and this is a third class lever. Now other simple machines such as a crank, a wheel, and an axle all work on a very similar system to what we just looked at. They're just mild or slight modifications. For example, a crank, here's the input and here's the pivot. So this is like a lever that just rotates. Okay, and here's your output here. So you have, this is the distance to the output, and here's the distance to the input. And so as you turn in a circle, it's just a continuous first class lever, where the output is always on the side opposite the input in relation to the pivot point. So a crank is a lever that rotates in 360 degrees, and they are designed usually to give you a large amount of mechanical advantage. This is an axle and a wheel. Here's the output here and the input here, and in this case, because of the design, there's actually no mechanical advantage. The axle and wheel is such that the mechanical advantage is less than 1 because of the design. And then again, a pulley is a situation where you have one rope on each side. Now here you have just one rope here, one rope here. These two distances are the same, and so the mechanical advantage is 1. This is an ordinary pulley, and generally pulleys are used to lift heavy loads. Now, there are ways that I'm going to show you in the next slide to improve your mechanical advantage. And that's these various pulleys. You have 3 pulleys here, okay? And the way to determine the mechanical advantage of the pulleys is to count the number of ropes that are pulling up on this wheel, because each one has the same tension in it. So for example, in this first situation, you have a force of 2T and a weight of W. Now you're pulling with a force of T, but you're getting 2T out of it. So 2T divided by T, the mechanical advantage is 2. This is in B, you have 3 ropes that are pulling up, 1 rope down. So the force up is 3T. The force down, or the tension, is 1. 3T divided by T is equal to a mechanical advantage of 3. Lastly, this one, instead of the person pulling on it pulling down, they actually pull up as well, so you have actually 1, 2, 3, 4 up ropes. And the mechanical advantage is then 4. And that's how a pulley works. This shows a picture of a forearm, and a forearm is an example of a third-class lever. You have the weight here, the pivot point is at the elbow. Here's the center of gravity for the arm. So you have, all of these are down. So this is this times this, and this times this are the two torques caused by the weight of the arm and the weight of the book. The only upward force is here, and it's actually closer to the pivot point. So the mechanical advantage here is going to be less than 1. And it pulls up this way. And here it shows the same thing more simplified. You have the upward force. This force here is not, you don't have to take that into account because it's at the pivot point, so it's multiplied by 0. So it's going to be 4 centimeters times FB is going to equal 16 centimeters times the weight plus 38 centimeters times the weight of the book. Now here's an example of a person picking up a box, and they show you here the pivot point is right here. Now the person lifting, the force lifting the box is right here. And it's a total of 8 centimeters from this pivot point. And this has to overcome his weight and the weight of the box. So you have 0.35, which is the distance here, times 55, which is his weight, times 9.8. Whoops. Times 9.8 plus 0.5 times 30, which is the weight of the box, times 9.8 equals, and this is the 8 centimeters here, times FB, which is the force that pulls back and lifts the box. And if you do the calculation here, you get 4,200 newtons. So that ends our lectures today. It's a short lecture period this way. Go through the homework problems, and if you have difficulties, just make sure you send it to me, and we'll work through the problems in class. Thank you.